Drop a watermelon onto concrete at 170 miles per hour and it shatters on impact. Strap a 500,000-pound commercial jet to its back and it absorbs the blow without leaving a scratch. This collision happens every single day at airports around the world, completely without incident. The only thing sitting between the aircraft and the tarmac is about 45 inches of rubber. Drive down any highway, and you will eventually see the shredded remains of semi-truck tires that blew out under pressure. A semi-truck carries immense weight, but it travels horizontally. An airplane carries an entire fuselage of passengers and cargo while effectively falling out of the sky. Surviving a vertical drop of that magnitude means aircraft tires cannot simply be thicker versions of the ones on your car. They require an entirely different class of engineered architecture. The foundation of an aircraft tire starts with a precise blend of proprietary synthetic rubber compounds formulated to resist extreme wear. But the rubber alone would fail on impact. Below the surface sits a structural skeleton made of embedded aluminum steel cords. Layered directly over that steel framework is a tight weave of nylon and aramid fabrics. These woven fabrics give the tire the immense tensile strength required to keep the outer rubber from rupturing outward when the plane touches down. Before a new design ever reaches a runway, manufacturers put prototypes through rigorous stress tests to push these materials well past their structural limits. They are subjected to intense speed and pressure evaluations, culminating in a simulated load capacity of up to 38 tons per tire. When the rubber hits the runway, it is this aerospace-grade woven armor, acting as a structural cage, that keeps the tire intact. A heavy-duty cage needs internal support. Commercial aircraft tires are never inflated with regular, oxygen-rich air, but exclusively with nitrogen. Nitrogen is an inert gas, which makes it highly stable. Because it lacks moisture, the nitrogen inside the tire is highly resistant to the massive temperature swings and atmospheric pressure shifts a plane experiences climbing to 30,000 feet. A standard car tire sits around 32 psi, and a semi-truck operates near 100. The airplane tire dwarfs them both, towering at 200 psi. Maximizing this internal pressure translates directly to maximizing the tire's ability to support 38 tons of metal. The rubber and steel provide the exterior shape, but the ultra-high-pressure invisible gas trapped inside acts as the primary pillar holding up the jet. On the outside, plane tires look quite different from what you see on the road. They skip the blocky tread patterns of car tires entirely in favor of deep, straight grooves. Cars require those block patterns to grip the road during sharp turns and variable maneuvering. An aircraft has a much simpler operational path. Its tires are engineered almost exclusively for rolling in a straight line during takeoffs and landings. The street grooves serve a vital safety purpose, rapidly evacuating standing water. Hitting a wet runway at 170 miles per hour creates hydroplaning risks. The deep channels give this water a place to escape, maintaining the tire's physical contact with the tarmac. Every millimeter of the tread is stripped of standard automotive features and optimized to prevent a single point of failure during the descent. A commercial jet typically relies on a set of about 20 tires. They endure roughly 500 touchdowns before they have to be pulled for maintenance. The tires positioned at the nose of the plane handle the steering friction, meaning they wear down even faster than the rear gear. Swapping a wheel is a labor-intensive process, requiring up to an hour of work for 2 mechanics. To execute the change, they lift a specific section of the 500,000-pound aircraft a mere 5 centimeters off the tarmac. Before the mechanics can even remove a wheel, they follow a critical safety procedure, bleeding the internal pressure from 200 psi all the way down to 30. This mandatory deflation neutralizes the immense stored energy inside, removing the risk of the tire exploding while the mechanics remove the retaining nuts and bolts. The tire's sheer power dictates its entire life cycle. It requires a highly controlled physical environment just to be handled safely by humans on the ground. A single tire core can go through up to 7 complete retreading cycles before its aviation days are over. Eventually, the structural integrity of the internal materials is compromised, and the wheel is reclassified as scrap rubber. But those robust materials find an unexpected second life. They are recycled into thick farming equipment treads, or ground up into soft, bouncy playground mulch. A farm tractor operates at a crawl, completely disconnected from the violent, high-speed impacts its recycled tires were originally designed to withstand. A piece of engineering built to repeatedly survive falling from the sky eventually retires to the dirt, having silently absorbed the most extreme physical forces in modern transportation.